Hello and welcome back. In the previous video, we discussed the first law of thermodynamics, and in this video, I want to talk about the second law. But to understand the second law, we first need to understand a concept called entropy. And you've probably heard entropy described as being a measurement of the disorder inside a system. And you've probably thought to yourself, well, what exactly does that mean? And to understand what we mean when we talk about the disorder in a system, we first need to understand the concepts of microstates and macrostates. Now, a microstate is a state that is defined by the microscopic properties of the system. So, for example, when we're looking at a gas, a microstate is defined by defining the positions and velocities of every single molecule inside the gas. A macrostate, on the other hand, is a state that is defined by the macroscopic properties of the system, things like pressure, temperature, and the number of atoms. Now, an important thing to understand is that there are generally a very, very large number of microstates that result in the same macrostate. In other words, there are a lot of different ways that I can define or assign positions and velocities to molecules and still wind up with the same pressure, temperature, and number of atoms. Now, a very common example that people give for understanding microstates and macrostates would be like a whole bunch of coins. Okay, so if I had a table, imagine you have like 1,000 coins that are sitting on a table. The macrostate would be something like if you counted up how many coins are heads up. And the microstate would be if you numbered each and every coin. So you said this is coin 1, 2, 3, 4, and you said, well, coin 1 is heads up, and coin 2 is heads, and then coin 3 is tails. Okay, so a microstate would be like defining the heads or tails for every individual coin, and the macrostate is just looking at the big picture, just how many of the coins are heads up. And what we mean when we talk about the uncertainty in the system is that we say that when a macrostate has a very, very large number of microstates that describe it, we say that the system is in a very uncertain system. That is to say that by measuring these macroscopic properties, things like pressure, temperature, and the number of atoms, there's very little that I can say about the actual microstate that I'm in, because there are so many different microstates that would result in that same macrostate. Just like if I had a whole bunch of coins, let's say I had 1,000 coins, and I told you that 500 of them are heads and 500 of them are tails, there are a lot of different ways that you could flip coins and wind up with 500 heads and 500 tails. So it'd be very difficult to say exactly which coin is heads and which coins are tails. So there's a very large number of microstates that describe that macrostate. On the other hand, if I told you that I had 1,000 coins and they're all heads up, you could immediately tell me what the microstate is. You could say, well, coin 1's heads up and coin 2's heads up, and you could go through all of them because you know that all of them have to be heads up. So examples of entropy, if we look at liquids, for example, liquids have a very large entropy, and the reason that they have a large entropy is because the positions of the atoms are so large. So, for example, if we compare this with or we contrast this with something like a crystalline solid, so something like salt or something like that, the atoms inside a crystal are basically fixed. So the atoms inside a crystal can't be just anywhere that they want to be. They have to be at very certain positions. So as a result, there's a limit on the number of microstates that can describe things like solids. However, liquids, the atoms can be basically anywhere that they want to be. And because the atoms can be wherever they want to be, there's a larger number of microstates that can be used to describe a liquid. The same thing goes for gases. If you fill up a glass with liquid, if you fill it up halfway, then you know all the liquid's going to be in the bottom half and that the top part's going to be empty. But if you fill up a glass with gas, the gas will fill the entire volume of the container. So as a result, there's more possibilities for the positions of the atoms inside a gas than there are for liquids. So gases have a greater entropy because there's more microstates that can describe a gas. Finally, when you heat up objects, you also increase the entropy. And the reason is that you have more energy that you can distribute between the particles, right? So we've talked about this before, that the kinetic energy of a gas is related to its temperature. So if I have a very, very cold gas, then that effectively creates like a speed limit for the atoms. So no atom can go faster than a certain speed because then it would use up all of the energy that we have. Similarly, if I have a very small amount of energy, I have a small amount of energy that I can distribute among my atoms. So there's a limited way that I can do that. However, if I have a very large amount of energy, then I have a lot of different ways that I can distribute the energy. So basically what the second law of thermodynamics states is it says that entropy will never decrease. So the entropy of a system is always either increasing or it's staying the same. So to understand this, I'd like to go back to the example of coins. So if I had a box, let's say, and it was full of 1,000 coins, and all of those coins were heads up, we would say that's a very, very low entropy state, okay, because I know exactly what the state is. All of the coins are heads up. Now, if you take that box of coins and you say, shake it up just a little bit, then almost certainly the entropy of that system will increase. Right? So almost certainly some of the coins that were heads up are going to flip over and they'll be tails. So the entropy of that system will increase. And if you keep shaking the box over and over again, the entropy of the system will almost certainly continue to increase until it eventually reaches a point where the entropy is really no longer changing. So eventually the entropy gets to a point where it's almost exactly, in the example of the coins, you've got almost half of them heads up and half of them in tails. And so when you shake the box, the entropy might change a little bit. It might go up a tiny amount, it might go down a tiny amount, but it's never going to change by a very large amount. And when you have something like gases, like for example, if I had Avogadro's number of coins and I'm shaking it up, then the entropy might increase or decrease once it gets to this point where the entropy is almost maximized. But the entropy is never going to change by an amount that is large enough to be measured. So when the entropy starts to reach that point where the entropy is maximized, then basically the entropy doesn't change. And sometimes people will say that the second law of thermodynamics is a statistical law or a probabilistic law. That is to say that it's not deterministically true, it's only probabilistically true. However, the important thing to understand about the second law of thermodynamics is that if the entropy of the system ever decreases, because the entropy is almost at its maximum, it'll never decrease by an amount that is measurable. It's probabilistically impossible that the entropy would ever decrease by an amount that you could ever measure. So at this point, I think I'd like to end the discussion of entropy and the second law of thermodynamics, and in the next video, I'll talk about the third law of thermodynamics and engines.